Hello everyone, welcome back to the course Electrochemical and Economic Aspects of Hydrogen Energy. For the past couple of classes, we have been discussing the basics of life cycle assessment. And in the current class, we will see the application of life cycle assessment to the hydrogen energy systems. What are the type of outputs that I can get from doing an LCA for hydrogen energy system? So, we will be taking a couple of case studies and trying to see the results that we can derive. And also in some of the studies, we will be integrating with the techno-economic results or the economic results as well to give you more clarity. Let's discuss a couple of case studies with respect to life cycle assessment. So the first case study that we are going to discuss is with respect to production of hydrogen or ammonia from biomass. So why ammonia? Like ammonia is, again, as you've understood, one of the largest chemical that is produced globally, and it also is produced majorly from natural gas, where it tends to consume almost 5% of the natural gas available and leads to 1.2% of the global GHG emissions. And again, 80% of the ammonia goes into the fertilizer industry, and as such, like, it also has a significant carbon dioxide footprint. So we wanted to see like if we can have a supply chain from biomass to ammonia, and this is what we have discussed in the previous classes as well. And we wanted to see this with a comparison of 3 different cases. So we wanted to see, to make up a case for biomass to ammonia, where the biomass could be housed at 3 different places globally. So we selected the straw as a biomass for India, eucalyptus as a biomass for Australia, and bagasse as a biomass for Brazil. So we wanted to see if the same process, which is biomass to hydrogen leading to ammonia production, was to be set up in 3 different places in the world, how would the techno-economics and how would the life cycle assessment or the emissions change or differ among themselves. And also you would see that the different biomasses that we selected have different supply chains. Now if I talk about the rice straw, this is basically a farm waste which is available in plenty but a scattered resource. Then the second resource is eucalyptus in Australia, which is basically an energy crop specifically grown on a dedicated land, not a byproduct. And the third one, which is bagasse in Brazil, is basically industry waste. So they have huge refineries in Brazil, where they have a lot of bagasse getting generated, and this is currently being used for cogeneration plants, but there could be other uses as well. So we wanted to see the effect of supply chain as well as far as this biomass is concerned. So the very first place was simulating these processes for production of hydrogen. So we had this process supply chain. I wouldn't go into much of the detail, but this all again was done in Aspen Plus, as was discussed by Ankur in the previous classes. So the process involved is you would have some kind of gasifier leading to production of syngas, and this gas would have some amount of methane which needs to be reformed. Then you would have the water gas shift reactor, then a PSA for the removal of CO2, and finally what you have by this time is almost pure hydrogen with some amount of nitrogen that is needed, and you would go into the Haber-Bosch loop producing ammonia. And we had the 3 different configurations of the process, which I am not going much into detail. So the first thing could be the process economics, which is calculated something similar to the way we have learned in the class, and we can see that economics could be very different for the different countries. So if I select wood or eucalyptus on the different supply chain on the basis of ammonia production in Australia, the cost could be quite high, or it is the largest. And again, the largest one is given to the capital recovery that is coming from the capex. So on the y-axis, what you have is the ammonia production cost in terms of dollars per ton of ammonia. If you consider the process again for India, which is using straw, and the price comes out to be quite economical, roughly of the order of $700, whereas the typical ammonia market price is around 500 or so. So it's quite economical in that sense. Brazil tends to stay somewhere in between. So one thing that we learn is like the price is highly dependent upon the country that you're looking at. It's not that if something is going to be economical in India, it's going to be the same way around in different countries as well. It could have a lot of things that play a role, and what you see on in the colors are the different aspects that have been considered in this study. Then when I do a life cycle assessment, again it's the cultivation of biomass, transportation of the biomass. Then this is a type of gasifier that was used, which is called a dual fluidized gasifier, but there will be a lot of reagents that go in and out of it. Then you would have the gas conditioning, because the syngas that you're coming needs to be made a good combination of hydrogen and nitrogen, for which you would need a lot of catalysts, a lot of utilities in terms of steam, storage, refrigeration. And then you would have conventional ammonia loop, which is a Haber-Bosch, the Haber-Bosch process producing in ammonia product. So, if I look at the global warming potential, it comes mainly from the electricity production. So, this is the process for Australia where wood is getting used. So, the processes are almost similar, but you can see which are the processes, like it can come from the electricity production, the transportation, the cultivation, the charcoal or the rape methyl ester that goes into it. So, it helps you quantify which are the regions that are causing majority of the emissions. Further, an interesting result comes in with respect to the ozone depletion potential. Now, ozone depletion potential has been compared for the 3 different biomasses, which is wood, straw and the gas. So, if I consider the case of Australia, the ozone depletion potential is mainly coming from the road transportation. If I talk about India, it is mainly coming from straw cultivation. If I talk about Brazil, it is coming from electricity production. So, this is an interesting result where you see that the majority of the emissions for a particular impact category can come from 3 different processes in 3 different countries. So, that is why we cannot say that if a process is found to be sustainable in Australia, it is going to be equally sustainable in India, because the emissions could be very different. Further, you can also basically try to see that converge all the results into single point category. So, here we have done all the results as an endpoint into a single point. The results given in here are the conventional steam methane reforming and the partial oxidation base ammonia production, which vary from 1.8 to 3. And you can see that no matter how we are producing it, like we have significant emission reduction if all the results are quantified into one indicator. But we see that Brazil tends to have a major advantage and India seems to have the least advantage as far as the emissions are concerned. Further, we can also see these results in terms of analyzing both the economic and the environmental parameters. So, what you see in this graph is a global warming potential in kgs of CO2 equivalent per kg of ammonia on the x-axis, and what you have on the y-axis is the ammonia production cost in dollars per kg of ammonia, and here are the results. So, this is the result for India, this is for Australia, and this is for Brazil. So, what you see here is in India you can produce biomass to hydrogen ammonia quite economically, but the emission reduction is not much because we are using a lot of grid based electricity that is coming from coal. Whereas in Brazil it is quite expensive, but the emissions are quite less, and again there are different features that lead to this emission, but one of the major factors is the electricity that is available in Brazil is quite cheap. If I talk about Australia, you get none of the advantages, which is it's expensive as well as the emissions are quite substantial as well. So, this is how you learn that like there are substantial changes in terms of both emissions and economics as you move from one country to another, because all the different processes could have different supply chains and there are different factors that are going to play a role, and that is why in-depth techno-economic and LCA should be carried out with respect to country specific, and this is what we have tried to equip you in this course as well. Now, let us take another example where we are doing an economic and emission analysis of green ammonia production through the electrolysis route. So, the process again is you would have an electrolyzer, a PEM based electrolyzer in here, which is basically taking in the deionized water and taking in electricity and producing hydrogen. So, here you can also see the BOP, and then you would have this ammonia production loop in terms of the Haber-Bosch process. Again, this process was modeled in Aspen Plus, which you have learned a couple of classes back to make up for the mass and energy balance. So, once you have the process ready, the electricity for this running of the electrolyzers can come from different sources. It can come from grid where it is available for 24 hours a day. It can come from a dedicated solar plant where we are assuming that it will be operating for on an average for 7 hours a day in India. It could be a mixed grid which has 24 hours of operation where it is running 7 hours of solar and 17 hours on grid, and it could also be an off grid plant where you would have 24 hours operation where 7 hours come directly from the grid and the rest 17 hours you would have a good battery system, which is basically a dedicated system which is basically trying to make up the energy requirement during night time as well. So, in 3 of the 4 cases you are running the plant for 24 hours, in one plant you are running it for just 7 hours. And we wanted to see how does the economics as well as the emissions change for these kind of pathways. So coming with respect to the economics first, so if I am talking about the grid based system which is running 24 hours, you can see the operating expenditure is the one that is basically dominating the yearly cost. So majority of it is going to the operating cost. Why? Because we are taking electricity, we are buying electricity from the grid, and that is going to be a major expense. So roughly for 1 kg of hydrogen I am using 55 to 59 units of electricity. So that is going to be a major expense, and of course you have capital expenditure here as well. If I go towards 7 hours of operation from solar, again my capex increases vastly. Why? Because now I would have to set up a big solar plant which is going to meet up the demand for it, and the OPEX reduces drastically because I am not importing any electricity, I am not buying any electricity for the yearly operation. Or the only thing that I would need is water and some of the other chemicals which are quite cheap. So as such my operating expenditure has gone down vastly. Then there could be a third pathway where I am going 7 hours with solar and 17 hours from grid. So in this case the capex remains the same as the earlier case because I still have the solar plant which is able to provide me electricity for 7 hours. For the rest 17 hours I am buying the electricity from the grid, and this is why you see an increase in OPEX occurring here. The fourth one would be where I am operating the plant in so called of green energy, where the solar plant is now much bigger in size and so is the battery backup. So herein I have assumed to be much bigger plant which has having solar which is now backing up the solar for the remaining 17 hours as well, and there is a huge battery capacity as well, and my OPEX has gone down significantly as well. So this is with respect to the yearly cost. If I talk about the levelized cost of ammonia, which is basically the addition of and the division of the ammonia production, like the yearly cost divided by the ammonia produced each year, this is how the cost would vary. So on the last I have also given the cost for conventional ammonia which has been taken to be $500 a ton or $0.5 per kg. So if I talk about the grid based ammonia, it's roughly of the order of $1.1 per kg, which is almost double and than that of the conventional ammonia, but it increases to almost 1.9 if I am going with only solar, that's operating for 7 hours. If I go with solar plus grid, means 7 hours of solar and 17 hours of grid, the cost again comes back to almost $1.1. And if I want to go for completely off grid, the cost is roughly $2 per kg of ammonia. So in that case, what are the insights that I can get from this kind of analysis? One is the comparison between this scenario which is running 7 hours of solar and 24 hours and solar plus batteries. Given that I am getting almost similar result with levelized cost of ammonia, I would always choose to run a plant on solar only, because even with battery backup I am investing so much of the money and still the levelized cost of ammonia isn't reducing. So it's always better to go with only operating the plant for 7 hours in a day, let the plant stay idle for the rest 17 hours because it's not giving me any cost advantage. So a better investment in terms of cost, in terms of making up a big solar plant and a battery backup doesn't hold much of value for me because battery storage is quite expensive. So this is one of the insights that I can get from this study. Further, some of you might of the opinion like there could be significant revenue from oxygen sales as well, because electrolyzers are going to produce both hydrogen and oxygen. Even if this oxygen sales are considered, the costs are going to come down, but there's not going to be much drastic reduction that is going to occur. So even if I take a very inflated price of oxygen like $100 per ton, the price is not going to come down very heavily. The interesting result would be if I would want to see these results overlapped with the CO2 emissions. So what you have on the y-axis on the left is the levelized cost of ammonia in dollars per kg. What you have on the y-axis on the right is the CO2 emissions in kgs of CO2 per kg of ammonia, and then you have the different cases in here. On the right hand side are basically the conventional cases where you are producing hydrogen or ammonia through either natural gas, coal or fuel oil. The price is assumed to be $500 per ton and the emissions can vary from 1.6 to 3.8. Now if I would want to compare that with the 4 cases that I have devised, which is basically using electricity for PEM electrolyzers leading to hydrogen and then ammonia production. For the grid based cases, of course the cost which is given in the blue bar increases, but the emissions are significantly higher, almost 4x as compared to the conventional case. Why is that of the case? Because I now have a lot of uncertainties in the system. I presently have a coal based grid wherein the power plant that are producing electricity are not very efficient either. So I am having significant emissions in the coal extraction. conversion of coal into electricity. Then when the electricity gets transported from the power plants to the endpoint in the grid, they are roughly 20% of the grid based, and there are going to be grid losses in that case. And this is where, and further, when I am using electrolyzers, the efficiency is almost around 60%. So I am using losing great amount of electricity down there as well. So this is why like you have a huge footprint in here. Now if I go with the solar operating for 7 hours only, the price of course is 4x, but the emissions are not exactly zero here. Why the emissions exactly not zero here? Because there is a lot of embodied emissions in here. What do I mean by embodied emissions? Because the solar panels during the construction have used silica, have used wafers, which have used different grades of energy in different places, and this is something that needs to be accounted for. And again, when you dispose of these solar panels, there are going to be emissions. So this is where you are getting these emissions of the tune of 0.4. I can run this plant for 7 hours of solar and 17 hours of grid, but again the emissions come down, but still they are way higher. I can go for an off-grid system where I have a solar plus batteries coming in. The emissions further rises because now I would have to make for emissions for the huge amount of batteries that is coming into play as well. So this is how we should be careful when we are doing an analysis which is the most sustainable pathway, because the different pathways could have economic advantages and still others could have environmental advantages, and we would have to see the trade-off between the two. We can have a look at another case study where I am basically cracking ammonia for producing hydrogen for refueling of the vehicles. So this kind of phenomena is normally gaining traction in the European countries because they do not have a very good hydrogen supply chain, but they do have a very good ammonia supply chain. So what they want to see is to at the onset, till the hydrogen storage transportation network is not set up, why not just transport the ammonia to the refueling facility, crack the ammonia there itself and refuel the vehicles. So this is the analysis that we did, wherein we are more concerned about ammonia cracking at the refueling station, so that I do not need to store or transport the hydrogen, and just crack the ammonia at the filling station and fill in the vehicles. And also we wanted to see how does that compare with the traditional approach where you would have the hydrogen produced through PEM electrolyzer, hydrogen storage and hydrogen dispensing. So this is the analysis that we did with respect to India, and let us see what the results are. So again, this analysis, again the simulations at the backward done in Aspen Plus, where you can see this is the reactor modeling for the ammonia cracker reactor, because ammonia crackers are not readily available in the market today and the data is quite scarce on that. So this is where the process modeling can help you out. They can help you ascertain the heating profile and the different losses that are expected to occur in the process. So if I look at the results on the right hand side, the results are basically with respect to direct hydrogen system. So what you have in here is the SMR based hydrogen, and this is the hydrogen that is produced from natural gas based steam methane reforming, transported, compressed and filling in the vehicle. If you see the current cost, the levelized cost of hydrogen is roughly of the order of $4 and the emissions are of the order of 13.5. If I go with solar based hydrogen generation through PEM water electrolysis, then followed by storage, transportation and dispensing, the cost goes quite high of the order of almost $12 per kg of hydrogen, and the emissions come down to almost 1.2, which is given in the red dot. Now compare that with ammonia based systems. Again the ammonia can come from either grid, solar, grid plus solar, solar plus batteries or conventional ammonia. So you can see that like almost all of these cases happen to be much more expensive as compared to the SMR based system. And if I talk about the emission reduction is also not very substantial. There are only two cases where you can have emission reduction, which is the solar and the solar plus batteries. In the case of solar plus batteries also, the emission goes as low as 3.2, whereas it goes only till 10 kgs of CO2 equivalent per kg of hydrogen in case of solar plus batteries. So this might not be a very good option for India, and this is the results that you get from an in-depth techno-economic and life cycle assessment, where you can see like whether a particular pathway that you are envisioning might make economic or emission sense for the Indian case or not. Also, you can also try to understand the emissions that are occurring on the other fronts, like there could be other emissions with respect to eutrophication, human toxicity, water use, particulate emission. So just to give you an example, so say if I compare the electrolytic hydrogen versus SMR, the electrolytic hydrogen tends to have a much greater water use as compared to the SMR based. Further, if I talk about ammonia based systems, it could have much greater emissions coming in terms of eutrophication as well as human toxicity. So these are some things that we need to be careful of, and a life cycle assessment basically helps you highlight some of these factors. So then we can also do a life cycle assessment with respect to hydrogen storage. So this is the preliminary results of a study we carried out at IIT Roorkee. So here we wanted to see the life cycle emissions from the construction and the disposal of the different storage methods in terms of the type 1, type 2, type 3, type 4 cylinders, liquid hydrogen cylinders in terms of aluminum tanks, and metal hydrides, two types of metal hydrides in magnesium hydride and sodium aluminum hydride. And the function rate for this case was storage of 1 kg of hydrogen. So we can see that the different kinds of storage could have very different emissions coming from different aspects. So if I talk about the global warming, the least one was coming for the type 2 cylinders, and then there could be other emissions that could come. So I'm not going to detail, but like this helps us also choose the sustainability of the hydrogen storage, where we have the construction of the cylinders, the use of the cylinders or the other storage mediums, and the disposal of the cylinders. Then we can have another case study where we would want to see like the complete life cycle of a hydrogen refilling station, where you would have solar PV modules filling in for production of electricity, going to a PEM electrolyzer, storage, trucking, and going to the fuel station and filling it into a fuel cell electric vehicle. So if this was the case, the inventories would have a lot of case, because like in the dispensing station you could have different materials going into it. In the storage there would be entirely different materials, entirely different from the PEM EC balance of plant, and somewhat different for the construction of the PEM electrolyzers. So these are the type of inventories that you would have to make or build up for doing this analysis. So we did this analysis in Gabby software, and further the results could be somewhere given in here. So if I talk about the climate change, we would have the different impacts coming from the different phases, but we can see the majority of the impact comes from the PV electricity in the case of climate change. Whereas if I talk about the water use, it's basically the PEM electrolyzer that is getting used. If I'm talking about the human toxicity, it's mainly coming from the dispensing stations. So the different aspects of a life cycle of this process could have very different kinds of emissions coming in. Further, we would have like the different impacts on a normalized front. So what you see here is the relative impacts of the different impact categories. So these were the impact categories that was considered in this study, and there could be different relative impacts as well. We can also compare these impacts with the traditional SMR based system again, which are given in the case of the dark blue color in here. So you can say, if I considering the case of global warming, which happens to be I2, I'm bringing down the emission, so if I'm considering the category I2, which is the global warming potential, you would see that I am bringing down the emissions significantly in terms of the CO2 emissions. But we also need to be careful that there are certain emissions where the emissions are also going up, specifically for I11 and 12. So if I see, but there are also going to be certain emission categories where the emissions are going slightly highly up, and this is specifically true for I14. And what is I14? It's basically the water use. So in water use, you would have a great amount of water use that is way larger as compared to the conventional SMR process. So these kind of analysis helps you understand the trade-off that occurs between different pathways, all of which might appear sustainable at the face value. Then I will also try to end up with this last case study, which is respect to energy storage. Now if we are going to go towards renewables more and more in the future, we would need energy storage for sure. And because majority of the renewable energy like solar and wind are intermittent, I need to go for grid stabilization. There's also going to be peak demand. I would want to go for energy resilience as well. And whenever I talk about storage, the first thing that might come to your mind would be batteries. But that's not the only options available. There could be other option in terms of molten salt storage, pumped hydro storage, redox flow batteries, as well as compressed air storage. So we did an in-depth techno-economic and life cycle assessment for these storage options. So just to give you an idea of these different storage options, when I talk about pumped hydro, it's basically akin to a normal hydro plant, but whenever you have excess electricity available through solar or wind, you would have a pump which will be pumping the water from a lower reservoir to an upper reservoir, and whenever you need electricity, you just let the water flow through the turbine and generate electricity. So this is what I mean by a pumped hydro system. So when I say battery energy system, you are aware of it. All of you would have seen inverter batteries in your in your homes. Majority of you would have seen, and you are well aware of this system. So what we did try to analyze were two kind of batteries. One was lithium ion batteries and the other one was vanadium redox flow batteries. Then the third option was the use of molten energy storage, wherein the sunlight or the direct solar radiation would be used for increasing the temperature using a solar concentrator, and then using some kind of phase change material for raising the temperature to 500 degrees Celsius or so. This material stays at a elevated temperature for quite some time, and during the night time you can use this high temperature material for raising the steam, generating electricity, and when the temperature is cool you can heat it up again during the daytime. The fifth option that we compared was that of compressed air. So akin to pumped hydro, whenever you have more excess electricity available in the grid, just compress air in some kind of underground reservoir, and whenever you need electricity just expand this air, run turbine and generate electricity. As such, the efficiency of this plant is roughly of the order of 60%, so not very great. So you can do this analysis with respect to the life cycle assessment, where you would want to consider the construction phase, the use phase and the disposal phase of the different options. So let me directly jump to the results in here. So if you would want to compare the different options with respect to levelized cost of storage and global warming potential, so you would have the global warming potential given on the x-axis and the levelized cost of storage given on the y-axis. So you will see that the pumped hydro and storage seems to be the best option, as well as both global warming potential and the levelized cost of storage is concerned. Batteries, both lithium ion and vanadium redox flow batteries, tend to have greater emissions, as well as the economics is not very favorable as well. If I talk about from the economics point of view, compressed air and molten salt storage happens to be almost comparable to pumped hydro. So these are the kind of analysis that can help you, that you can do with in-depth techno-economic analysis and life cycle assessment of different systems. So in this class we have tried to understand the different trade-offs with the help of results of life cycle assessment and techno-economic analysis with respect to hydrogen energy based systems. With this we take a break for the current class. Thank you.